Hello everyone, my name is Yuchen Lu. I'm a student from Cornell University. Today I'm going to talk about optimal complexity in decentralized training. This is a joint work with my advisor, Chris Dessa. In this talk, I will be focusing on three fundamental questions. I'll start by introducing a layer taxonomy that describes different decentralized machine learning systems, and then I'll be discussing the theoretical limits for such systems, and finally, I'll introduce two optimal decentralized algorithms that converge at the optimal rate, which closes the gap towards the theoretical limits in terms of iteration complexity. For starters, let's look at this motivating example. Suppose that we have some data set gathered from the nature and a model to train. Usually the size of the data set can be very large, so we need some resource from either public clouds or local clusters. So let's say we have a number of GPUs run from AWS or Google Cloud. And then a standard way to utilize these resources is to use a fully centralized data parallel solution. Specifically, we let each worker in the system maintain a copy of the model parameters and an optimizer. We pre-process or transform the data set, upload them into the cluster, shuffle them, and load them into different workers. And then workers compute the stochastic gradient on the data shards, and then use the OREDUCE to get the average gradients over the entire system. This is a fully centralized solution because if we split the system stack into different layers, we can see that this system uses a centralized method in different layers. In the application layer, the dataset is shuffled and gathered in a central cluster. In the protocol layer, all the workers communicate using the OREDUCE to get the average gradients, or sometimes we use the parameter server. In the topology layer, all the workers in the system are fully connected in the sense that any two workers in the system establish a communication channel, and each worker in the system send and receive messages from all the other workers. This is an elegant but not ideal solution because in many cases, a shuffled dataset is hard to obtain, and when the network is high latency or low bandwidth, we cannot really afford to perform the OREDUCE operation or maintain a complete graph topology. There are many different lines of research that shows that if we can decentralize the system in terms of layers, we can get some benefit. For example, in the application layer, a series of work, especially, for example, the federated learning talks about we can leave the data on the edge devices without uploading them into the data center so that we preserve the privacy of the raw data. In the protocol layer, a series of works discussed using GOSSIP protocol to replace the OREDUCE, which shows that it can balance loads and mitigate the ill-conditioned networks. And finally, in the topology layer, another line of research discussed using arbitrary graph topology to replace a complete graph. For example, on a ring graph where any workers are connected to two neighbors. And I'd like to point out here that the implementation of decentralization in different layers are orthogonal. For example, we can still implement OREDUCE on a ring graph or using GOSSIP on shuffled data. And here is an example of to show how we can make a fully centralized system in a fully decentralized one. From 1 to 2, if we let all the workers maintain their own local data set, the system becomes decentralized in the application layer. And then furthermore, if we sparsify the connection, the system becomes decentralized in the topology layer. And finally, if we replace the OREDUCE with the GOSSIP, we can get a fully decentralized system in 4, which is decentralized in all 3 layers. Decentralized training is popular in the research community. Many upper bounds on the iteration complexity are shown. But a question that left open is what is the optimal complexity on the iteration complexity for different algorithms, and how far away we are from such optimal complexity. This question has been answered partially by some of the previous work. They provide analysis on stochastic, non-stochastic, or strongly convex problems. They are great, but still leave the central question open because in practice, many problems of interest are non-convex, for example, DNN training, and in many applications, we usually use the stochastic algorithms, for example, SGD. And finally, as we mentioned before, a system can be decentralized in terms of different layers. So how would such optimal complexity adapt to different layers remains unclear. To answer all these questions, we start by formulating the problem into a standard empirical risk minimization framework. We denote the bold X to be the model parameters, which is d-dimensional. We let n to denote the number of workers, and fi to be the loss on worker I. And we wish to find a stationary point x hat, where on x hat, the loss function has small gradient norm in expectation. And then we go through some assumptions in different layers. First, in the application layer, we assume the loss function to be smooth non-convex and range bounded. And also, we assume that each worker I can interact with the gradient oracle gi tilde, where the oracle is unbiased and variance bounded. These are pretty standard assumptions in the domain of stochastic non-convex optimization. And then additionally, we need another assumption that to bound the data heterogeneity on different workers. A commonly used one is the first inequality, where the full gradient on worker I and full gradient over the entire system is bounded by some var sigma square at any point in the weight space. This is a strong assumption, especially when workers maintain their own local data set. So instead of using this, we assume a different assumption, which is shown below, where we only assume a bounded variance at 0.0. So as we are showing later, even with this weaker assumption, our complexity bound has a smaller dependency. And then we move on to the protocol layer. We assume that the entire system is synchronous, and we have an extended discussion for asynchronous algorithm in the appendix of the main paper. In each iteration, we assume the workers have B query budgets to stochastic gradient oracle, and the updates must be zero respecting. A formal definition of zero respecting can be found in the main paper, but informally, it means that we assume only gradient steps or communication can modify coordinate of the model. So we can see that the zero respecting assumption does not specify how workers communicate. So further, we denote AB as a class of all algorithms fulfill the zero respecting assumption, but we use ABW to be the subset of algorithm that uses the gossip protocol, which is given a fixed matrix W if we denote YTI and ZTI to be the input and output of such protocol on worker I at tth iteration. The updated formula must fulfill the following, which basically just use the fixed matrix W to take the weighted average on the input in a neighborhood. We denote lambda to be the general second largest eigenvalue of W, and as we will show later, this lambda plays a crucial role on the upper bound of the iteration complexity. And finally, we denote G and D to be the class of topology graphs connecting n workers with diameter D. So here we show our main results on the lower bounds for two different cases in theorem 1 and corollary 1 in the main paper. So if we do not specify a protocol in the protocol layer, we get the first bound, which is decentralizing both application and topology layer. We can see the complexity bound has two different terms. The first term relates to the oracle variance and gradient query budget, so we call that sampling variance, sampling complexity. The second term relates to the graph-related parameter, so we call that communication complexity. And we can see that the query budget, gradient query budget only can reduce the first term, but is invariant to the second one. And there's a trade-off between these two terms. When the size of the system is small, we can see the first term dominate in terms of the epsilon, but when the system scales, i.e. when the number of workers increases, the second communication term will become the designing term gradually. If we constrain the protocol layer to use a gossip, we can get another bound in terms of the spectral gap of the gossip matrix. We can still see the sampling complexity remain the same, but for the communication complexity, the lower bound depends on the 1 over square root of the spectral gap of the gossip matrix. So that now that we have the lower bounds, we can show many state-of-the-art decentralized training algorithm has a certain gap in terms of complexity. Here I list some representative algorithms and their complexity under the same assumptions. We can see that they match the lower bound in terms of sample complexity, but they have a certain gap in the communication complexity as shown in the last column. So where does this gap come from? Here we take a closer look of what a worker does in each iteration on over a timeline. So in each iteration, a worker does two operations. The first one is some computation, for example, backpropagation on a mini batch of examples to compute the gradient. And then it participates in the communication to perform a communication round. So if we use or reduce in the communication protocol layer, then at the end of each iteration, all the workers will have perfect consistency on the model parameters so that it does not affect the backpropagation in the next iteration. However, if we use gossip protocol in the communication in the protocol layer, then the adjacent gradient in the next iteration will be computed on a noisy or lack of a consistency model. A naive way to mitigate this is to add some communication rounds between two iterations, but doing this would compromise the throughput because we are using more communication, we are consuming more bandwidth, but we are not making further progress on the optimization side. So how can we do this? In the paper, we propose a different paradigm called the biphase communication. So the basic idea is that because we need consecutive communication rounds, we can first group the entire all the iterations on the timeline into different groups, and we call these groups phase. So here we show an example of phase length r equals 2. At the beginning of each phase, we denote the M to be the model that are being trained, and we make a copy of that model and denote that as M prime. And these two models participate in parallel. That model M only participate in the communication protocol, while M prime only participate in gradient computation. We can see the throughput remains the same compared to the previous decentralized training algorithm, because in each iteration, we are still performing one round of communication and one backpropagation. And at the end of the phase, we use the gradients computed on prime to update M, so that we can see that because M is went through the consecutive communication rounds, then it reached certain level of consistency before being modified by the gradients. So now that we have introduced the biphase communication, the question remains how we can modify an existing decentralized training algorithm to use such paradigm, and how would such paradigm lead to the optimal complexity. The first algorithm that we propose in the paper is called de facto, which relies on a very simple idea. It relies on a factorization technique in the graph theory. So the basic idea that we can find R different matrices that corresponds to the graph, which can factorize the average matrices. Which means that if we let M go through R consecutive communication rounds in one phase, then at the end of the phase, all the workers will reach perfect consistency on the model parameters like all reduce do. So equivalently, this algorithm, statistically, this algorithm is equivalent to all reduce with additional batch size of R. This is a good solution, but not ideal, because now the phase length is fixed to be R, and this is still a centralized system in terms of the protocol layer. So we can implement it on a decentralized application or decentralized topology, but the protocol layer is still centralized. So can we just make the system decentralized in all three layers? And this comes to our algorithm 2, which we call detect. So if we replace the communication round directly with a fixed matrix, it does not need to optimal complexity. In the paper, we discussed using two more techniques. One is the accelerated gossip which is shown in the algorithm 3, and a gradient tracking, which is shown in algorithm 2. And we show that using this biphase communication along with these two techniques will lead to an optimal complexity. And we also found that the optimal phase length relates to the mixing time of the Markov chain the gossip matrix defines it. And for a detailed description of the theorem, please refer to the paper. And with some theoretical analysis, we can see that the two algorithms de facto and detect, they both can reach the lower bound in terms of iteration complexity with only constants or logarithm gap. If we look at the communication complexity of a detect, we can see that it basically improves upon the previous communication complexity on two sides. First, it pushes the data heterogeneity bound epsilon 0 into a log, and then it also reduces the power of the spectral gap of the communication matrix. So accordingly, we conduct some empirical analysis on these two aspects on two different tasks. In the first task, we train a Linnet on CVPRW 10 with different shuffling strategy, and we can see that when the data become more heterogeneous and less shuffled, detect converges faster compared to other baselines. And second, we also train a ResNet on CVPR 100 under different spectral gaps. We can see when the spectral gap becomes small, detect converges faster and more stable compared to the previous baselines. Thank you. This concludes my presentation. Please feel free to stay connected and join us in the live discussion. Thank you.